Hi. We're going to convert the labels that you see at the top of the columns in, for example, Excel or any other spreadsheet manager to the number from that of that column in the whole sheet. It might sound straightforward. A to the end of the alphabet is 1 to 26, and then we go to AA for 27, and then AB, and so on. It's actually deceptively simple, and the solution is also simple. But what's actually going on is interesting. So let's start off with the A and Z. Those are really easy. If we look them up in the alphabet, we get 1 and then 26. Then it gets more interesting because the next one after Z is AA. That's 1, 1. But it's supposed to be 27. Clearly, this is kind of a positional system. The further left a character is, the more significance it has, but it's not just base 26 because there's no 0 here. It does, however, work if we say this is in 1, 1 base 26, because that's 1 times 26 to the power of 1 plus 1, that's 27. So if we evaluate this in base 26, we get the right result. Where things get really interesting is what actually happens when you have a Z. So this gives us a 26. 26 is not a valid digit number in base 26, just like 10 is not a digit in our normal decimal system. We only have from 0 to 9. Zeros are skipped here because we never get anything that has the index 0 in the alphabet. So what's actually happening here when we evaluate this in base 26 is that APL allows digit position values to have a number that is higher than the base. And it just overflows with a carry to the next position. So when we have 26 ones, then that overflows to become, well, 26 plus 1 times 26. If it was 126, here it's implicitly 0.26, so that overflows and just becomes 0 plus 26. And so that actually works. And if we do this also with, say, AZ, where we get 126, then this means there are 26 ones and 126, so that's, we just add them together. And we get 52. And if we had a B here, we would add that together again. So this is 126 and then two 26s. And if we go up to even larger numbers here, then we'll see how the carry is going to carry over. So there are 26 plus 26 26s, and so on. And it doesn't matter that it will overflow to the next position. We just add them all up. We do the multiplication with the powers, and then we add it all up. So we can write our full solution to the problem as we're binding the alphabet as left argument to the lookup function, iota, and then we evaluate in base 26. So that's our solution. We can put in anything here and get the right result. To really understand what's going on, it might be a good idea to kind of emulate the functionality of the base evaluation here, also known as decode. So what's actually happening? Let's go back to these numbers for a moment. Is we get these three values here, and this is all base 26. So these are the ones, these are the 26s, and these are the 26 squareds. That means we can get the powers by starting off with three numbers like this, we can reverse them because we have descending powers. These are the highest one, and then they are too high by 1, so we can subtract 1 here. And then we have 26 to the power of that. That gives us the weights for the positions, and then we can multiply by our numbers and sum that. Or alternatively, we could use an inner product to do this. And that is actually what's happening here, that we're taking the length of the argument and finding those powers and then just adding it all up. And it doesn't matter that they are too large, that they overflow, and it couldn't really be represented in that system. So we can write this here as quad A. We're looking up the right argument, and over here, instead of iota 3, we have the tally of the argument. So now we can do APL over here. Of course, there's no reason to actually write this because we have the primitive that does this, but this could help give an understanding about why this works, even though we're using digit position values that are actually too high for the number system. Thank you for watching.